Is the audio working? La la la. All right. Let me begin here. I'll start with a word of prayer once I settle down. Oh man. Oh, what? Oh no. Oh, phew. Thought I was missing something. All right. I'll begin. Heavenly Father, we thank you for this day again. I thank you for this class and these students. And I just pray that you'd guide our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me continue with our look at theorem, theorem 3.8.4, which is on the various equivalence. So we're studying V equals to the sum of these K subspaces, right? And we're trying to understand what it means for them to be independent subspaces, right? So last time I talked to you guys about the proof of 1 implies 2, and I think today I won't do everything here, but I will, I think, do 2 implies 3 because it's a little bit interesting. And so let's start with that. So this is the proof of 2 implies 3. So we assume that Wj intersect with the sum of everything except for J is 0. All right? And we assume that for each J, with the obvious meaning. All right? Now, then we pick X in, so our goal, we're trying to show implies 3. Just to remind you, 3 is that V is the direct sum. So 3 is that V equals to W1 plus circle W2, direct sum WK. And the definition given in my notes for what the definition is of this is that there exists, it's that for each X in V, there exists unique X sub I in Wi for which X is equal to X1 plus X2 plus plus XK. All right, that's actually the definition that's given in my notes for the W being the internal direct sum of V being the internal direct sum of W1 through WK. All right. So we're trying to show 2 implies 3, which means we're trying to show that no matter which X I pick in V, there exists a unique X sub I and Wi for which X is formed by the sum of those guys. So the proof goes like this. We have to pick an arbitrary element X in the vector space. All right. So we let X be an element of V, right? And which of course is equal to W1 plus WK, right? So that implies that there exists X sub I in Wi for I equals 1 to K such that X is equal to X1 plus X2 plus plus X sub K, right? That's just definition of the whole vector space being the sum of the subspaces is that we can do that. And then what we're going to do, okay, so at this point we have existence. Existence is almost assumed for us already, right? Like it's the existence of the xi, it's already given to us in that the presupposition of the theorem is that. The issue is uniqueness, that there exists unique xi, right? So how do you prove uniqueness for something? Well, you suppose you've got another choice, right? So let's see here, we'll do that. Suppose you have y sub I, an element of wi, you know, such that what? X is also equal to y1 plus y2, right? Suppose you got another choice, possibly different. All right. So and then what follows is a little bit sneaky. So if I was asked to prove this on a test and I was a student, I would have gotten all this fine. And then I would have got stuck exactly here if I hadn't studied. I would personally have to memorize the next thing. This would be the thing I memorized for the sake of my test, you know? Observe, this is a sneaky step right here. X sub j is equal to x minus the sum I not equal to j of x sub I. And also, you can do the same thing for y sub j, right? Y sub j is equal to x minus the sum I not equal to j of y sub I. All right, so you got that. Continuing over here, we can look at y sub j minus x sub j. What do you get? So we just copy those down, take their difference. What do you get? I'll write it out. X minus the sum I not equal to j of x sub I, y sub I rather, minus parentheses x minus the sum I not equal to j of x sub I. The x's, they be canceling, and we actually just have what? The sum, I'll do minus the sum of I not equal to j of y, I'll tell you, I'll forget the minus, let's just flip it around. X sub I minus y sub I, right? Are you guys with me? Can you tell me where that is? In the sum of what subspaces is that? Notice that this is an element of W1, everything except for the jth one, right? It's not an element of W. It's in the sum of the other subspaces except for J, right? But on the other hand, over here, this is manifestly an element of Wj, right? So this vector is in both the sum of the subspaces other than J, and it's in the jth subspace. Therefore, what? Yj minus xj equals 2? What did we assume? The intersection of Wj with all these is 0, right? So this vector is in both Wj and all of those. Therefore, it must be the 0 vector, which of course then tells me that xj is equal to yj for all j. And that completes the proof of 2 implies 3. because we've showed that there's a unique decomposition into the vectors in each subspace. Now I'm going to skip over to the proof of 4 implies, or rather 5 implies 1, because I think that one's interesting. So here we're assuming that if x of I is an element of Wi, for I equals 1 to k, and then x1 plus plus xk equals to 0 implies x1 equals to 0 all the way out to xk equals to 0. So that's what that's the statement of 5, all right? So if you look at my notes, I've proved, in fact, that, 3 implies 4, and then 4 also implies 5. 4 was the statement that if you take the union of the bases in the subspace, you get a basis for the whole space. Now 1, let us remind ourselves what 1 is. What are we trying to show? So we'd like to demonstrate, we'd like to show that pi, a mapping from W1 across the Cartesian product k-fold subspaces here to V, defined by pi of the k-tuple x1 through xk, and it's defined to be like that. We're supposed to, our claim is that this is an isomorphism. We're supposed to show, let me say it this way, we wish to show this is an isomorphism. All right? So how do we do this? Well, I guess first of all we should prove it's linear, right? So you guys remind me, if I have, suppose I have, x and y in here, right? And C in the field of scalars, if we look at cx plus y, that's what? That's c times x1 xk plus y1 yk. How did we define addition in the direct product? Remember, we just do it component-wise, right? So I got cx1 plus y1, cx2 plus y2, cxk plus yk. All right? So what does that tell me about the product, the pi of cx plus y?
It's equal to cx1 plus y1 plus cx2 plus y2, and so on.
Very good. And then what can I do? How about I factor c out, right? And then I write the y terms over here. I mean, why not, right? And that is c times pi of x plus pi of y. So, yay, it's linear, right? We've shown that it's a linear transformation. Can you guys tell me how to show it's onto? I'll just say this, pi is onto because we supposed that W is equal to W1 plus WK. So X in V, that's supposed to be a V. X in V has X equal to X1 plus da da plus XK, right? Thus, pi of X1 comma XK is equal to X for any X. Any X in V. Sorry, my language is not optimal here. I might take a point off my test if I was to write it quite like this. I'm not entirely satisfied with the structure of the sentence there, but that's the idea. How do I show it's, so that's onto. Again, it just rests on the assumption that V is the sum of the subspaces. And to show it's one-to-one, what should we do? Yeah, I need to, exactly. Somehow or another, I need to use that. But if I want to show directly that it's one-to-one, what should I look at? The kernel, right? So let's let X be an element of the kernel of pi. Then pi of X, which is equal to X1 plus da 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 plus XK, is equal to 0. That implies that X1 equal to 0, down to XK equals to 0. Therefore, X is equal to 0. Therefore, the kernel of pi is equal to 0. Consequently, pi is one-to-one. Therefore, pi is in isomorphism. So there it is. So there are some interesting things we do later on which rest on this this notion. Okay, guys. Let me show you I'll show you my two favorite examples. So like I don't have many examples with more than two subspaces. Most of my examples actually just involve a decomposition into two subspaces. Is not like k of them, but it is nice to have the theory for k things. But man, you did get the middle board, right? Okay, just checking. Example 1. How about we could look at Rn by n and W1 equal to like A in Rn by n such that A transpose equals to A, and W2 A in Rn by n such that A transpose equals to minus A.
Very similar to a homework problem.
Uh-oh. Well, at the risk of doing your homework, I'm going to say a little bit more. Notice that A is 1/2 of A plus A transpose plus 1/2 of A minus A transpose. Therefore, W1 plus W2 is Rn by n. Since I just showed an arbitrary matrix can be written as the sum of a symmetric and an antisymmetric matrix. If A is an element of W1 intersect W2, then A transpose is equal to A is equal to minus A. But that implies that A is equal to 0, W1 intersect W2, 0. Therefore, Rn by n is the direct sum decomposition of symmetric and antisymmetric matrices. Simple as that. Example 2. If I look at my vector space as being the set of real valued functions of a real variable, right? Fr. So that means we're looking at functions with domain the real numbers. Well, check it out. I can write f of x is 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. I'd like here, I'm writing both of these examples one after the other because I want you to see this is the same trick. Right? I say same, but it's not really the same trick. But it's the spirit of these two examples is the same. So I've added 0 in a suspicious way, right? You can check that this is an even function. You can check that this is an odd function. Right? So this is an element of the sum of the odd functions, even functions, plus the odd functions. What happens if you assume that your function is both even and odd? It's 0. Yeah, well, let's find out. So suppose f of x is an element of the even functions intersect the odd functions. And I'm just calling w even and w odd as the names for the set of even functions and the set of odd functions, right? So that would mean that you had, well, it's almost the same calculation, right? F of x is equal to f of minus x, but it's also equal to minus f of minus x, right? This is for the even. This is the definition of an odd function, right? That f of x is equal to minus f of minus x. But the only way that this can be true, of course, this implies that f of x is equal to minus f of x for all x, which then tells you that f of x is equal to 0 for all x in R, right? Which tells you that f is equal to 0. So in summary, the intersection of the even and the odd functions is 0. And we can see that the function space is the direct sum decomposition of even functions and odd functions. Now, this example is very, very different than the first one, right? The first one, I have tasked you with the onerous problem of writing down the basis for this, right? Unfairly on your test 1. I just added the unfairly for effect. I don't really believe it. But, you know, in the homework, I think you had symmetric. On the test, I think I gave you antisymmetric. I forget. Maybe it was vice versa, flippity flop. But you've actually written down bases for W1 and W2, right? I could not ask you to write down the basis for W even or W odd because this is an infinite dimensional example. So one thing I like to always point out here is an example of this is like the exponential function. I don't know if you guys ever seen this before or not, but I don't know, it makes me happy. So e to the x is equal to 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. Recognize that cosh is the even part of the exponential, and sinh is the odd part of the exponential. So here's this algebra in play. Anyway, so just a couple of examples. So now let's talk about what it means for us if we've got a linear transformation which has this, which has subspaces which are invariant. Remember last time we talked about a little bit about, not a lot, but I defined invariant subspace, right? So I think what I'm going to do for the purposes of class, at least to simplify things a little bit, is I'm just going to take the case of 2 subspaces for the sake of the in-class discussion, but the notes treats k subspaces, okay? But I think you guys will have an easier chance of following my argument if I reduce the number to 2. So that way, instead of having like a double index, we're just going to use like 2 different letters for the 2 different bases. I think you'll follow it easier. So this is not in the notes exactly what I'm about to do, but the notes have something more gory in general. So here we go. So let's suppose we have T is a mapping from V to V, and let's say that V is the direct sum of W1 and W2, all right? So it's the direct sum of these two subspaces, right? Where, I'll just set some notation up here. Let's say W1 is like the span of beta 1, and W2 is the span of beta 2, where let's set some notation down. Beta 1, let's say it has V1 out through Vn, and beta 2, let's say it's got, oh, I don't know, W1 out through W K. Oh, I don't want to use K. M, there. M as in mommy, N as in nano. All right, so we got these two bases for these two subspaces, and they're a direct sum decomposition, right? But also, and we're assuming something, T of W1 is a subset of TW1, and T of W2 is a subset of W2. In other words, I'm assuming both of these subspaces are T invariant.
You wrote T of W1 is a subset of.
Oh man. Whoa.
That's technically true.
Whoa. Whew. I did something like this in physics not long ago. This is actually kind of tame compared to what I did there. So, all right.
Also something that was true but not useful.
No, it was just crazy. It was just straight up insane what I wrote in physics. TW1, subset of W1, TW2, subset of W2. So this means, in words, that W1 and W2 are so-called T-invariant subspaces. It turns out there are many interesting T-invariant subspaces that we can study, right? So this is something we're going to see, put into action before long. So what I want to study is, what does the matrix of T look like if we use the basis which is formed by just taking the union of 1 and 2. So we let beta equal to beta 1 union beta 2 with the natural ordering, right? Let us look at what the matrix of T with respect to the beta basis looks like, right? So we'd have T of, let's see here, V1, right, with respect to the beta basis. And next, we'd have T of V2, but I'll skip that and go straight ahead to the interesting part. T of Vn, N as in nanu. So that's the beta 1 part. It's the beta 1 part. Next up, you got your beta 2 part. So the coordinate vectors of T, so they got TW1, the beta, whatever the words, coordinate of that. And then finally over here to TWM, coordinate vector of that. Right? So how does this work? Let's think about it. So I'm gonna write a comment under this, and then what I'm gonna do is I'm gonna write a comment like here, and then I'm gonna continue the equality down here. So notice for these that T of Vi is an element of the span of beta 1. And these ones over here, T of W, let's say J, is an element of the span of beta 2, right? Excuse me. So what does that mean about these coordinate vectors? Let's see here. So phi beta of v1 equals to e1, right? And so forth and so on. Phi beta of vn is equal to en, right? What is phi beta of w1 equal to? En plus 1, right. And so forth and so on down the line. The Wm would be En plus m. So can you see what that means? Like the coordinate vector of t of vi, right? It's an element of the span of your E1 all the way out to En. Whereas over here, the coordinate vector of twj is an element of the span of, you know, En plus 1, En plus m, right? So that means that, to put it into words, this is only non-zero in the first n rows, and this is only non-zero in the last m rows. So what that means is that the matrix looks like this. Let's say A1, A2. And we can prove, in fact, that the form of these matrices is precisely the restriction of T. Well, it's not the restriction, actually. It's what I'm going to call is TW1. TW1 with respect to the beta 1 matrix. And over here you've got TW2. Now what do I mean by TW1 and TW2? That was supposed to be both ones. My notation's kind of dumb, right? I write beta 1 comma beta 1 and beta 2 comma beta 2 and then beta comma beta. What's the book write? It just writes beta, right? Because I do two things when one will do. I do two things because I want you to, you know that when I have beta gamma and I have beta beta, it's logically the same thing. It's just, just you happen to have the same basis for the domain and the codomain. Now, so the definition here for TW1 is just this. TW1 is a linear transformation from W1 to W1. And how is it defined? Well, T of x is equal to T of W, my bad. T of W1 of x is equal to T of x for all x in W1. The same for W2. Why is that? Why can we define that? Why is that reasonable? What are we assuming about T and W1 and W2? We're assuming that W1 and W2 are invariant subspaces, right? So that's why I can reasonably define T sub W1 and D sub W2. I would say that it's just the restriction to W1 and the restriction to W2, but that's not quite right, because the restriction, as we construct it, still has the same codomain. So the codomain would still be V if I just talked about the restriction. So it's the restriction to W1 with the codomain squashed to just W1, But there it is, like, this is it. And this is pretty cool, right? So if you have invariant subspaces, and you have decomposition of those for your space, matrix or linear transformation has this block diagonal form. That's the main that we know how there is is to